Cyclotronic Propulsion Space Engines, Innovation in Space Exploration. Cyclotronic propulsion is an advanced technology that utilizes the principles of cyclotrons to generate thrust in space. This form of propulsion promises to revolutionize space transportation systems by combining high fuel efficiency with the ability to achieve significant speeds in the vacuum of space. Below, we will explore in detail how this technology works, its advantages and applications, and why it could represent an important step in long-range space exploration. 1. Cyclotron Principles Applied to Space Propulsion. The cyclotron is a type of particle accelerator that uses a magnetic field and an alternating electric field to accelerate charged particles, such as protons or electrons, to speeds close to the speed of light. In the context of space propulsion, this concept is adapted to launch particles at high speed, and according to Newton's third law, action and reaction, this generates thrust in the opposite direction of the emitted particle beam. In a space-based cyclotron, fuel is converted into a stream of charged particles, which are accelerated in concentric spirals inside the cyclotron. Once they reach maximum speed, these particles are expelled through an exhaust nozzle, creating a continuous thrust. Although the mass of the emitted particles is very low, their extremely high velocity compensates to generate effective thrust, especially in long-duration missions where efficiency is prioritized. 2. Advantages of the cyclotron as a space engine. One of the main benefits of a cyclotron-based engine is its fuel efficiency. Unlike traditional chemical rockets, which burn large amounts of fuel to generate thrust in short bursts, the cyclotron uses a small amount of mass, fired at extremely high velocities, to generate thrust continuously and sustainably. This approach is particularly useful in deep space missions, where fuel resupply is limited and the priority is to maximize thrust per unit of expelled mass. The cyclonic propulsion system is also durable. Because there is no need to burn large amounts of fuel at each stage of the mission, the engine can continue operating for long periods with low resource consumption. This makes it an ideal option for long-duration missions far from the solar system, where refueling is impossible. Additionally, since the particles accelerated by the cyclotron reach near light speeds, the engine can produce sustained thrust that allows spacecraft to achieve significant speeds over time. Although the initial acceleration might be slower compared to traditional rockets, the constant thrust of the cyclotron would allow the spacecraft to reach extremely high velocities on long-distance trajectories, such as missions to other planets or even nearby stars. 3. Particle material selection for propulsion. The fuel used in a cyclonic propulsion engine is essentially any type of matter that can be ionized and accelerated. However, the type of particles selected directly affects the system's efficiency. Protons are an ideal choice due to their favorable mass-to-charge ratio. As positively charged particles, they are easily manipulated by the cyclotron's electric and magnetic fields. Another potential material could be ionized gas such as xenon, which is already used in conventional ion engines. This gas is easy to store, relatively dense, and can be ionized and accelerated with great efficiency. Additionally, with a higher atomic mass than hydrogen, it produces more thrust per emitted particle. 4. Atomic battery is an energy source. To power the cyclotron and associated control systems, a constant supply of electrical energy is required. In missions near the Sun, solar energy could be a viable option, but in deep space or distant orbits, sunlight is too weak to provide sufficient power. For this reason, the use of an atomic battery, RTG, is ideal for these missions. Radioisotope Thermoelectric Generators, RTGs, convert the heat generated by the decay of radioactive materials, such as plutonium-238, into electricity using thermocouples. This system is highly reliable, produces constant power for decades, and requires no moving parts. This energy is sufficient to continuously power the cyclotron, ensuring the viability of the propulsion system over long missions. 5. Cooling in deep space. One of the challenges of using a cyclotron and an RTG is the amount of heat they generate. However, the vacuum of space offers a unique advantage. Its proximity to absolute zero allows for efficient heat dissipation through radiators. Radiators exposed to the cold of space can dissipate the heat generated by the cyclotron and RTG through infrared radiation. As the spacecraft moves further away from the Sun, the radiators become even more effective, as the ambient temperature decreases. The optimized design of these radiators ensures that the spacecraft can maintain its operating temperature without overheating. allowing the cyclotron and RTG to operate continuously and efficiently. 6. Unmanned design for initial phases. To simplify the initial development of the system, the first spacecraft using cyclonic propulsion will not be manned. This eliminates the need for complex life support systems and shielding for human protection. Instead, the focus is on protecting the electronic systems and key components of the spacecraft. Using shielding against radiation and heat, the spacecraft can be remotely controlled, and the protection system is specifically designed to maintain electronic controls and internal structures safely, without the need for human isolation systems. This allows for faster and more efficient testing before considering the possibility of manned missions. 7. Particle beam safety in space. A potential concern might be the impact of the particle beam emitted by this cyclotron. However, in the vacuum of space, there are no nearby objects that could be damaged by the beam. Since space is virtually devoid of matter, the particles accelerated by this cyclotron will travel without colliding with atoms or molecules, minimizing any risk of damage. Additionally, the direction of the particle beam can be carefully controlled to avoid any accidental impact with the spacecraft or other objects in space. This system ensures that the beam does not affect the spacecraft or its immediate environment. 8. Future applications of cyclonic propulsion. The cyclonic propulsion engine is ideal for long-range missions, such as flights to distant planets, moons of gas giants, or even interstellar missions. Its ability to maintain constant thrust over long periods makes it a superior option for exploring regions of space that would be beyond the reach of traditional rockets. As technology advances, we may see spacecraft with cyclonic propulsion capable of traveling beyond the solar system, opening new frontiers in space exploration and enabling unprecedented scientific missions.